In this video we will take a look at 3 things. Number 1, Introduction to Digital Twin and its architecture. Number 2, the Digital Twin Project. And, on number 3, the Machine Learning Model. Digital Twin. A digital twin is a virtual replica of a physical system, process, or asset that continuously receives real-time data from sensors and other sources. Also, to avoid misconception, a digital twin doesn't necessarily require a 3D model. The core idea of a digital twin is having a virtual representation of a physical system that receives real-time data from the physical counterpart. As long as data is collected, analyzed, and visualized, whether through dashboards, graphs, or any other form, it qualifies as a digital twin. The problem, and why it matters. Did you know that unplanned downtime, across industries like manufacturing, power plants, and MEP systems, costs companies an estimated $50 billion per annum globally? What if we could predict failures before they happen, and avoid these costly disruptions? Unplanned equipment failures can lead to massive financial losses. For example, in the oil and gas industry, a single day of downtime on an offshore drilling rig can cost between $500,000 to $1 million. A major energy company implemented digital twin for predictive maintenance, using AI and real-time data analytics, and so is reducing unexpected shutdowns and saving over $50 million annually. The question, why digital twin? And the answer is, managing complex systems efficiently is challenging due to unexpected failures, high energy consumption, and maintenance costs. A digital twin replicates real-world systems virtually, offering real-time insights, analysis options, and AI-driven optimizations. With ML integration, we can optimize performance across various domains, including HVAC, industrial automation, smart buildings, and power grids. And the options are endless. The digital twin architecture, depending project needs, usually consists of sensors installation, data collection and storage to local server, data transport from local server to cloud, data storage and processing to cloud, data transport from cloud to digital twin. Digital twin simulation and visualization, data transport from cloud to machine learning model, machine learning model training and interface, establishment of two-way communication between physical asset or system to digital twin and digital twin to physical asset or system. Machine learning model integration, for prediction and action, with digital twin and physical asset, or system. Feedback loop generation, for data collection, and continuous improvements. Listed are some of the technologies that may use to produce digital twin. Multiple sensors like CO2, temperature, humidity, airflow, pressure, vibration and many others. Communication protocols like Modbus RTU, BACnet MSTP, Zigbee, LoRaWAN, Wi-Fi, BLE and many others. Data collection protocols like MQTT, Modbus TCP, BACnet IP and more. IoT platforms like Node-RED, Telegraph, OPC UA, Azure IoT Hub, AWS IoT Core, Google Cloud, Things Board, Ka IoT and others. Visualization platforms like AWS IoT Twin Maker, Azure Digital Twins, Siemens MindSphere, Tendom, Granophon, GE Digital Twin, NVIDIA Omniverse, Unreal Engine, Unity and more. Local storage like InfluxDB, PostgreSQL, SQLite and more. Cloud services like Azure IoT, AWS IoT, Google Cloud and others. Protocols for cloud integration like MQTT over TLS, HTTP REST API, AMQP and more. Edge computing platforms like Azure IoT Edge, AWS Greengrass, Google Cloud and many others. Let's move to digital twin model. Currently our digital twin is offline. Let's connect it to physical asset to start receiving the live sensors data. Okay, now our digital twin is fully connected, and is receiving the sensors data in real time, successfully. Now, let's have a look at real-time sensor data received, of mechanical equipments. Following is the real-time sensor data, for air terminals. Following are the heat map of ducts and spaces, based on sensors data. For airflow, humidity, temperature, velocity, and vibration. Here is the data flow chart for streams. As told before, having the data on dashboard and charts only, is also a digital twin. Training the machine learning model, based on available sensors, what can we achieve? Energy consumption predictions. Forecasting energy consumption, based on the correlation between factors such as supply air temperature, humidity, airflow, and coil temperature. The goal is to optimize energy usage, by predicting when consumption will spike or drop, leading to more efficient system operation. HVAC system efficiency prediction. Estimation of efficiency of the HVAC system based on defined variables. The goal is to detect underperformance or potential faults in the system. Example, blocked ducts or malfunctioning components, by predicting expected performance and comparing it with actual performance. Air quality predictions. Forecasting CO2 levels in the air based on airflow, supply air temperature, and CO2 sensor data. The goal is to ensure that the indoor air quality is maintained within a safe range for occupants by predicting when CO2 levels may rise to unsafe levels. Vibration anomaly detection. Predicting potential failures in mechanical equipment based on vibration sensor data, along with temperature and pressure sensor readings. The goal is to detect early signs of mechanical failures, example, faulty bearings, misalignment, or unbalanced equipment, before they cause serious damage or downtime. Supply air temperature control. Predicting supply air temperature fluctuations, based on input from supply air temperature and humidity sensors. The goal is to maintain optimal air temperature and prevent overheating or undercooling in building spaces by adjusting control systems. Airflow optimization. Predicting airflow conditions, by analyzing supply airflow sensor, supply air velocity sensor, and supply air temperature data. The goal is to optimize airflow within the HVAC system to ensure that ventilation is balanced and consistent throughout the building, preventing areas of stagnation or overventilation. Preventive maintenance predictions. Predicting when equipment may need maintenance by analyzing trends in temperature, vibration, pressure, and energy consumption over time. The goal is to predict and schedule maintenance activities to prevent costly failures and downtime by identifying trends that signal potential issues. Humidity control. Predicting the forecast of indoor humidity levels, based on supply air temperature, supply airflow, and humidity sensor data. The goal is to prevent excess humidity or dryness, which can lead to comfort issues, mold growth, or damage to building materials. Fault detection. Predicting potential faults, like malfunctioning HVAC components, by correlating abnormal readings from the equipment temperature, vibration, air pressure, and airflow sensors. The goal is to predict failures before they occur and take proactive steps to repair or replace malfunctioning parts, ensuring the system operates smoothly. Performance benchmarking. Prediction by comparing current system performance, like temperature, pressure, airflow, with historical data to predict system behavior. The goal is to establish benchmarks for expected system performance, and flag deviations that indicate inefficiency, wear, or potential issues. Let's prepare the machine learning model, train it, verify it, and test it, based on real-time data being received from digital twin. Here is a source file, based on past data. Using it, we will train our machine learning model. The source file consists 10,000 rows of data. That's a good amount of data to train model. The model is being prepared using artificial neural networks, called ANN. The model learning is started. Let's prepare the model for prediction and accuracy. Model shows promising result with overall accuracy score of 97%. Now let's check the accuracy of each segment the model is trained for. And the results are exceptional, consists of accuracy from 97 to 100% for each segment. Let's test the model with received data and predict the output. And here is the output. An alert and action are created based on the results. Equipment and power failure are predicted, and automated actions are taken as a preventive measure of shutting down the equipment automatically on site. As model is ready and tested, afterwards we will integrate it with our digital twin for anomalies detection, predictions, automation and further facility management functions. That's it for the video. Hope you learned something and enjoyed it. Thanks for watching.